Hi students, welcome to Science Extension, and this is Module 1 where we look at the foundations of scientific thinking. Our first video is going to focus on what is science. This forms part of two sections that are part of Module 1, and the first of these sections is the development of modern science. We're going to have a little bit of a tour through the history and philosophy of science to try and understand how science has developed as a discipline and what are some of the key characteristics of scientific knowledge. To do this, we're going to be asking this question as our central question for this first series of videos and this first section of work, and that is, how have philosophical arguments influenced the development of modern scientific research? As with all of the videos that we've looked at, we want to have a learning intention, something that we want to try and keep in focus as we go through all of the key ideas in this video. And so in this one, we're going to see if we can explore epistemology and alternative ways of knowing, for example, the development of navigation. So to do this, we want to try and first of all look at what knowledge is, and that's going to link us into epistemology. We're going to try and identify the specific type of knowledge that science encompasses. What is it that makes scientific knowledge different to other forms of knowledge? And then we're going to see if we can put that into practice. We're going to look at a specific area of scientific development, scientific understanding, and how we can bring together those areas of history, epistemology, and science. The first thing that we need to explore is, what is epistemology? Epistemology is basically knowing about knowledge, or it's the study of the nature, the origins, and the limits of human knowledge. And I'm going to quote as much as I can from a range of different sources, because that is what this course is designed to do. It's designed to give you a taste of lots of different areas of science, lots of different types of science, and to get you to be a critical thinker about what science actually is and what it isn't, and where some of our important ideas come from. Epistemologists concern themselves with concepts such as knowledge, belief, epistemic justification, confirmation, and explanation. Epistemic problems include refuting skepticism, which is the denial that knowledge, either in general or in a particular area, is possible, by explaining why some beliefs and not others are justified. This probably sounds a little bit philosophical, and it certainly is. It's an opportunity for us to start to think a little bit more critically about what epistemology and about what knowledge in general really is. Historically, epistemology has included both philosophy and the natural sciences, which includes things like physics and chemistry, as well as biology and geology, and also ethics, logic, and metaphysics. Essentially, the field aims to answer the fundamental questions of humans: why are we here? Why are things the way they are? Does anything really matter? And so on. Natural sciences aim to answer the second of these questions using a system that science students will be familiar with, which we've often referred to as the scientific method. So Module 1 then, in I guess a more basic term, is a study of the origins of the scientific method. But instead of just accepting a textbook definition or a series of skills that are outlined in either a textbook or a series of slides like this one, what we're trying to do in this module is attempt to explain the rationale behind why we use the scientific method, why it isn't just a recipe book or a cookbook list of things to do in order to be doing good science, as well as some of the alternative methods that have that it has replaced or that have been refined over the years, and of course some basic ideas as to how that was developed. What we want is a theory of knowledge, because we want to be able to explain, in the face of skeptical arguments, how knowledge is actually possible. So our next little section should start to look at what knowledge is. And of course, you can spend an awful lot of time reading a lot of literature about what knowledge in general is. So I've picked a couple of things out for us to have a little bit of a look at in this section. There's many forms of knowledge, and of course many potential arguments about what constitutes knowledge. As we start to consider cultural understandings of knowledge and cultural development of knowledge, then this just continues to increase. Peter Reason and John Heron developed a theory of extended epistemology, which is based on 4 interdependent ways of knowing that they referred to as experiential knowing, presentational knowing, propositional knowing, and practical knowing. These 4 ways of knowing can be briefly defined both in terms of the process and the outcome. Firstly, experiential knowing is by being present with and direct face-to-face encounter with persons, places, or things. It's knowing through the immediacy of perceiving, through empathy and resonance. Its product is the quality of the relationship in which it participates, including the quality of being of those in relationship. Presentational knowing emerges from the encounters of experiential knowing by intuiting significant form and process in that which is met. Its product reveals this significance through the expressive imagery of movement, dance, sound, music, drawing, painting, sculpture, poetry, story, and drama. Propositional knowing about something is intellectual knowing of ideas and theories. Its product is the informative spoken or written statement. Practical knowing is the knowing how to do something. Its product is a skill, knack, or competence, interpersonal, manual, political, technical, transpersonal, and more, supported by a community of practice. Sloan, Perry, and Duncan in 2017 expanded on the Heron and Reason model. They primarily used this as a basis for a social context to broaden our understanding of knowledge. And they also described 4 interdependent ways of knowing. And you can see some relationship between the Sloan, Perry, and Duncan model and also that of Heron and Reason. You can see here we have foundational knowing, where there are at least 3 major foundations for how we make sense of the world: experience, indigenous or ancestral wisdom, and spiritual natural wisdom. Artistic knowing, to understand our experiences and to help others understand them, we create representations through story or visual art or movement or music and so on. Generalized knowing, which is when we look at patterns and experiment to create concepts, and this is where academic theories and propositions live, as well as theories of change, logic models, and promising practices. And practical knowing, where we act intentionally in the world in ways that are informed by our previous actions as well as our generalized knowing. We take our generalizations and turn them into practice. Now, the whole area of what knowledge is very broad, and it's a deep philosophical one, and it's certainly not something that we can solve in a small period of time, either in a video or in a class. But we do want to be aware of the fact that there are a lot of different ways of knowing, primarily because we want to be able to identify what science is or what science knowledge is and what it isn't. And therefore we can make some reasonable conclusions, or at least some logical conclusions, on the basis of information presented to determine whether that knowledge qualifies as scientific knowledge or not. Now, I'm not going to read through all of the components of this table because I'm assuming that you can read. And so therefore, what I'm going to do instead is just to describe the fact that there are 8 different ways of knowing here, in contrast to the 2 sets of 4 that I've given you already, each of which, and probably the top 4 are the key ones here, but each of which has a description and a purpose, but also some types of limitations, some areas where there can be questions about the type of knowledge or the way we might use knowledge in a broader sense. Pick, for example, emotion, which is a very nice, easy way of talking about knowledge in terms of how we make sense of ideas, experiences, or behavior. And emotions are very important in influencing our day-to-day decisions. Yet emotions are not something that everyone feels exactly the same way in response to exactly the same stimuli. And this is where the understanding or the study of knowledge can get a little bit cloudy and difficult for us to be able to reproduce in a scientific kind of way. So now we've got our little background in knowledge, we need now to move on to what science actually is. So how are we going to define scientific knowledge? Well, scientific knowledge is generally agreed to encapsulate the following 3 components: the qualities of scientific knowledge, the limitations of scientific knowledge, and how scientific knowledge is generated. Scientific epistemology specifically focuses on the nature of scientific knowledge. Norm Lederman and his associates have described in 2015 the key qualities of the nature of science. This has been refined over probably 30-odd years of investigation, research, and consultation with students and with science teachers. Their conclusions are that science is about the distinction between observations and inferences. It's about the distinction between scientific laws and theories. And certainly we use theories in a different way in science to what they are commonly understood to mean in day-to-day discussion. Even though scientific knowledge is at least partially based on and/or derived from observations of the natural world, that is, it's empirical, and we'll look at a lot more around empiricism in our next video, it nevertheless involves human imagination and creativity. Scientific knowledge is subjective and theory-laden. Scientists' beliefs, previous knowledge, training, experiences, and expectations, in addition to theoretical commitments, influence their work. This was a very important part of the Kuhnian structure of scientific revolutions thesis. Science as a human enterprise is practiced in the context of a larger culture and its practitioners or scientists, and these are the products of that culture. The scientific knowledge is never absolute or certain. This knowledge, including facts, theories, and laws, is inherently tentative and is subject to change. Akasha, in her excellent book, An Introduction to the Philosophy of Science, said one of the main tasks of philosophy of science is to understand how techniques such as experimentation, observation, and theory construction have enabled scientists to unravel so many of nature's secrets. Now, sometimes it can assist us to define something by identifying what something is not. Science has its limitations. It has limitations in a moral or ethical sense. What should science say about animal or human experimentation? And we'll explore this in future videos as well. Aesthetic statements. How can science measure the beauty of a painting, like a Rembrandt? Utility of scientific knowledge. What should science do about genetic disease inheritance? And we've certainly had a lot of movies dedicated to the misuse of genetic information. Supernatural phenomena. Where is the line between science and religion? The progress of scientific knowledge is both incremental and profound. The history of science is replete with examples of sequential developments in our knowledge and rare paradigm shifts where a scientific revolution has taken place. Probably one of the biggest ones that we know is the Copernican revolution. And that didn't revolutionize just science, but an entire world view of where we were, of our place in the universe. Scientific knowledge relies on sensory observations augmented by technological development, and our technologies have certainly allowed our senses to go in places they never would have gone before. Empirical evidence or experimentation, rational arguments involving logic and reasoning, and we'll look at both deductive and inductive reasoning in later videos too, and also skepticism. So that, I guess, brings us to a bit of a conversation around some of the misconceptions associated with science. And this little section looking at misconceptions will be something that I separate out into another video. So that brings us to the last section of this first part of Module 1, which is to see if we can bring together some of history, epistemology, and science as we look at the development of navigation and a very important man of history, John Harrison. Tracing the development of navigation is a good way to bring these different elements together because humanity has had a history of a nomadic lifestyle. We've always been travelers. The problem with traveling is it implies a way of locating a starting point sometime in the future. And that tends to involve two key concepts: the ability to visualize your surroundings. You need to know where I am now and where I am later, and then the ability to visualize a direction or determine some sort of way of figuring out which way I need to go in order to return to that original starting point. Broadly speaking, the first of these has been covered by map making. So if I make a map of where I am now with some of the key features and where I'm going, I can get a bit of a track of these sorts of things. But the second is navigation. I actually need to know which direction, not just that I need to go south, but I need to know which direction south is in order for me to actually travel south back to my original starting point. The early travelers were relying on their senses to observe landforms, wind speed and direction, tides, and measure distance to navigate. Many of the indigenous people, Aboriginal and Torres Strait Islanders and Polynesians, commonly use natural navigation aids such as the stars, ocean currents, and wind patterns. They use non-physical devices including songs or song lines, dreaming tracks, and stories for memorizing the properties of stars or islands or navigational routes. As dominant nations sought to conquer new lands, empires like the British, Spanish, and French sought to travel the seas. Celestial navigation using the position of stars, constellations, or the sun were the primary and long-held staples for navigation. In fact, one of the reasons why eye patches are synonymous with pirates was that one of the ways of trying to navigate at sea was to look at the sun, to basically get your bearings in terms of where you were going by navigating using the sun, which meant looking at the sun, even though there were sort of some devices that were designed to try and reduce some of the glare. It left a very large number of navigators, early navigators, with limited or no sight in at least one of their eyes. And the problem with most of these methods is they were pretty good for latitudes, they were pretty good for figuring out north-south, but not so good for longitude. That was a significant problem. Some of the advances in measuring techniques and geometry led to the development of more accurate maps, and also indicated the Earth was a sphere, despite the fact that some people still insist that it is flat. The altitude of the North Star in the Northern Hemisphere was very important for latitudinal information, but we were still struggling with the problem of longitude. In Davis Sobel's book on longitude, where she talks a lot about the history of this and also the contribution of John Harrison, very interesting little book to read. One of her quotes was around sea captains of the 15th, 16th and 17th centuries relying on a method known as dead reckoning to gauge distances east or west of home port. The captain would throw a log overboard and observe how quickly the ship receded from this temporary guidepost. He noted the crude speedometer readings in his ship's logbook, along with the direction of travel, which he took from the stars or a compass, and the length of time on a particular course, counted with a sandglass or a pocket watch. Factoring in the effects of ocean currents, fickle winds, and errors in judgment, he then determined his longitude. He routinely missed his mark, of course, searching in vain for the island where he had hoped to find fresh water, or even the continent that was his destination. Too often, the technique of dead reckoning marked him for a dead man. The compass was an important tool to orient travellers to the magnetic north, and unlike the sun, magnets worked at night as well as during the day. However, an incident in 1707 involving the loss of 4 English warships and 2,000 sailors due to navigation error led to the 1714 Longitude Act. Parliament promised a £20,000 reward to anyone who could solve the longitude problem, an enormous sum of money back in the 18th century. Such a prize drew luminaries such as Galileo, who used Jupiter's moons and his pendulum motion, which worked pretty well on land and not so well at sea. Christian Huygens, famous for the wave properties of light demonstration and also the clash he had with Isaac Newton over Newton's particle theory of light. And Huygens was the first to build a working pendulum clock, and also Robert Hooke, and he also had a clash with Huygens over who had the rights to the spiral balance spring, which was also important in the pendulum clock. Each of these considerable scientists put their intellect into the solution of this particular problem. The idea was that if a clock could be brought on board ship with the time set to the home port, then local time could be compared to the home time to work out how far around the globe they had travelled. Since 24 hours represents 360 degrees, simple mathematics would provide the relative longitude. Despite the immense scientific talent invested in solving this problem, no one had, and their failure to do so continued to inspire the astronomers to believe that comprehensive star maps might have been the answer. But it was John Harrison, an English clockmaker, who solved the problem, inventing a marine chronometer which was accurate to within 3 seconds per day. His first invention was used on the HMS Centurion on a voyage to Lisbon in 1736. Despite positive responses from the ship's officers, Harrison's clock was not aboard the HMS Centurion when it got lost in 1741 on sail to the South Pacific. Navigational error cost Commodore Anson many of his crew. Harrison's prototypes currently reside in the Flamsteed House at the Royal Observatory in Greenwich and are still operational. While Harrison didn't receive all of the £20,000 prize money, he did receive a better share than most of the other contenders, and his invention and subsequent refinements changed sea travel forever. Again, something very important in the field of science and technology that had massive implications not just on science, but on life in general. Since then, lots of important navigation instruments have been developed, including the astrolabe, the sextant, the chronometer, and chiplog, which were designed to identify locations in three-dimensional space. The information from these instruments has been used to produce highly refined maps. And today, they're even better. Modern navigation uses radar, gyroscopic compasses, and GPS to provide positional and kinematic, that is, speed and acceleration, information to degrees of accuracy unimaginable to the scientists of the past. This is how science, history, and epistemology move forward. And they also open up some areas for us to have a look at in future videos. Thanks for watching.